All right, so a continuation of our review problems here. So we're going to revisit this problem for, again, we sure have seen this problem a lot. All right, but very important for business students to look at. So this particular problem says that you're selling X is representing the number of digital cameras produced in a week. Price demand function is going to be given as P equals 400 minus 0.4x. Looks like our cost function, 2,000 plus 160x. And then we're given this domain that we should do this on. Okay, so first of all, when you're doing a revenue, you can think of I'll write it up here, a revenue is just equal to the number of items you sell times the price, okay, like a unit price for what you sell. So the number of items is X, well the unit price is the price demand function. So R of X is just equal to X times P. X is the number of items produced. P is the price demand function. So we'd have X times 400 minus 0.4x, that's it. All right, and what I'd probably do is just multiply that out. So we'll have the revenue function R of X is equal to 400x minus 0.4x to the second, okay? Okay, now we're going to do the profit function, and we know that profit is just equal to the revenue minus the cost. So we're going to have the profit function, I'll use with a capital P, is the revenue, which we just found to be 400x minus 0.4x to the second, minus the cost function, which was given as 2,000 plus 160x. And you want to distribute, collect like terms, and get a good answer to the problem. So we're going to have P of x is equal to 400x minus 0.4x squared minus 2,000 and minus 160x. Okay, I see students make this common mistake all the time on this. That's like a -1 multiplying by those, so it's changing those signs. So now we have, it looks like, we got two like terms. Okay, so let's write the profit function as capital P of x and put it in a descending order, negative 0.4x squared plus 240x and minus 2,000. Okay, so that'll give the answer to that. Okay, so all I did is just did revenue minus cost, had like terms to collect, and then I got it okay. All right. Okay. Okay, so now we're going to apply the calculus. What we'll be looking at is use calculus to find the maximum revenue. So if we're going to find a maximum on something, the procedure is the same. You want to go through and find critical numbers. So the first thing you want to do is, we're finding maximum revenue. We're not dealing with profit here. We're dealing with revenue. Okay, so we're going to do R prime of x. Okay, so the derivative of the revenue function that you have in the first answer blank is 400 minus, and by power rule, that would be 0.8x. Okay, so that is your marginal revenue. You want to set that equal to 0 to find critical numbers. So we're going to have 0 equals 400 minus 0.8x. Okay, this is going to find where the tangent line is horizontal. I'm going to move the 0.8 to the other side. I'm adding 0.8x to both sides to get this. Okay, then I will divide both sides by 0.8. And that will solve for x, and that'll give us a critical number that we're looking for here then. Okay, so taking 400 divided by 0.8 will give 500. So 500 is your critical number that you want to have then. Okay, so now what I'm going to do is we're going to make a sign chart. After we find a critical number, then the second thing we want to do, let's just look at a sign chart. Test the derivative on either side of the critical number, 500. So we know that the derivative is 0 at 500. We also know that this problem doesn't really make any sense unless x is bigger than 0. They also gave you a domain of this problem all the way to 590. So we're going to go up to 590. I'm not sure why that was given in the problem, but when we graph it, we'll take a look at that. Okay. So let's go ahead and let's do some test points then. So again, your derivative is this. So we're going to plug some test points into that derivative. And let's keep it simple. Pick a number between 0 and 500. Plug into the derivative. You'll have 400 minus 0.8 times 1. Okay, I think you can tell in your head that's positive. That means the function is increasing. Okay, let's take a test point bigger than 500 but smaller than 590. Let's take 501. So we have 400 minus 0.8 times 501. Okay, that's going to be a negative. If you're not sure, you could always go through. I need to change a few things on my calculator here. Okay, and clear this off. So let's just go 400 and then minus 0.8 times the test point 501. And that'll give you a negative number. Okay, so we get a negative. So that means the function is decreasing. All right, so really what this just means is the function's going to increase, hit a high point, then decrease like that. Okay, so that maximum revenue is going to happen when x is equal to 500. Okay, now if we're going to find that maximum revenue, you need to plug into the revenue function, which is our answer to part A. So we're going to do this basically, and then we'll use the calculator. So we're going to do 400 times 500 minus 0.4 times 500 to the second. Okay, and we'll get that. Okay, and that'll be the maximum revenue. So we know that it's 500 items is where the maximum occurs. So we just go 400 times 500 and then minus 0.4 and times 500 to the second power. And that will give the maximum revenue. So that looks like $100,000. Oops, hold on, that's not what I wanted to do. Okay, slide that way over there. There we go. Okay, all right. So we got our $1,000 for our revenue now. So that's the answer to that problem. And then we've already really answered the problem to part E also. So we want to record that the maximum revenue is $100,000. And how many cameras? Well, that's the 500. Okay, so if we make 500 cameras, that is what produces that maximum revenue. Okay. Now what we're going to do is we're going to figure out the price that should be charged to maximize revenue. Okay, this is simple enough. You've got a price demand function. All right. We also just figured out that 500 is the value of x that produces a maximum. So what we just do really is we evaluate the price demand function at 500. So we get 400 minus 0.4 times 500. Okay, and that'll take care of that price there. So let's say we get 400 minus 0.4 times 500 will give us a $200 charge then. Okay, all right. Okay, so we got this problem solved. Now what I'm going to do is I'm just going to, again, go through the importance of checking all this stuff on your calculator with a graphing. So this price would be $200 per camera. Okay, so that's the optimum price that will maximize the revenue based on this information. Okay, the other thing I would do on this now is on the graphing calculator, I would recommend that you graph the revenue. So I'm going to clear all this stuff off here. So the revenue is in part A, that's 400x and minus 0.4 x to the second. And we were told to go 0 to 590 on our window. So let's do that, 0 to 590. You can scale that by whatever you want to, maybe, I don't know, 30, 50, something like that would be okay. Let's go 50. And the maximum revenue was 100,000, so it makes a lot of sense to at least use 100,000. Okay, so let's let's go ahead and just do 100,000 and maybe scale that by 10,000. Okay? So with that viewing window, there's a good viewing window. If I graph this on the calculator, yeah, this is where your max is. I'm not really sure why I gave you the 590. I think it was intended to be 1,000. Okay, I looked at that and I just kind of thought, well, why did I do that? So let's go ahead and change this window to 1,000. Doesn't really matter because we're checking and verifying our answer anyway. So let's do our window like this instead. Okay, and then graph it. And let's see if this all makes sense to us now. Okay, so that's the viewing window I did here. The graph like this. Okay, now what we do on this is let's just trace it to 500. That's where we got the maximum revenue. You can tell that's a maximum, and you can tell that value is 100,000, so that verifies the problem. So you basically got 500 cameras, revenue of $100,000. Okay, you can tell visually that that's correct maximum. Okay, all right. So that's that typical kind of problem, a good application problem. All right, now we're going to move to indefinite integrals. So we learned a lot about indefinite integrals. So we're going to go ahead and work on this concept a little bit. All right, so these are just your basic antiderivatives. And you have a series of rules. We learned a series of rules. I'm just going to kind of review these things. So if you have an integral of just a constant times dx, that's kx plus c. Again, the derivative of kx is k. So that's how you can tell you're right. We also learned the power rule for integrals. So if we have x to the n dx, that would be x to the n plus 1 over n plus 1 plus c. In this problem, n, however, cannot be equal to -1. You run into a problem if you have that, although you can still do the integral. Then we have a bunch of antiderivative formulas, like the integral of e to the x dx is just itself. Whoops, don't need a dx, I need a plus c. Okay, we also learned that the integral of 1 over x dx is ln of absolute value of x plus c. So those were kind of the standard things, and there may be a few other ones that will pop up as we do these. Now, a problem like this could be done in your head. When we learned how to do integrals, we learned a series of rules. If you have sums and differences, you could actually break this up into 3 integrals if you wanted to. So we'll have like 2e to the x dx minus the integral of 1 over x dx, and then plus the integral of x to the 10th dx like that. Okay? Now you can also do this if you want to. You don't really have to, but you could bring out that 2. You can bring out constants that are multiplied by functions out of your integral like that. So we can do, these are all just basic antiderivatives using the formulas that we have over here at the right. Okay, so the first integral would be, just write down the 2. Integral of e to the x is itself. The integral of 1 over x is ln of absolute value of x. You need to have that absolute value because we don't really know what the value of x is, and it must be a positive number in order to do a natural logarithm. And then we have the power rule here, which we just go x to the 10 plus 1 over 10 plus 1. Now you just do this in your head. That's x to the 11th over 11. Okay, so you can write it that way, or you can say 1/11th x to the 11th plus c. Okay, now the nice thing about doing this is you can always tell you're right. So, and this one's easy enough to do in your head for the most part. I'll just check this over here though. So if we do the derivative of 2e to the x is 2e to the x. The derivative of ln x is 1 over x. Then 1/11th is a constant. The derivative of x to the 11th is 11x to the 10th. The derivative of a constant c is 0. So notice the 11's cross out, and notice this is exactly what your original problem was. 2e to the x minus 1 over x plus x to the 10th. So it's real simple to tell that you've done things right. Okay? Okay, next thing, you would need to multiply this out. So we're just going to multiply that out by FOIL, distributive property. First term would be t to the second. Outside term would be minus 2t. Inside term is minus 2t again. And the last term is positive 4. You can also do the shortcut. We've gone over in class on that too. Okay? So what we have is we have the integral, and that 4 can come out. And then we have 4 times the integral of t squared minus 4t plus 4 times dt. Now you can split this up into 3 integrals if you want to, but you don't really have to because you can do this in your head. So what you would have is 4. Don't forget about the 4. Now let's just apply the rules. Power rule for t squared would be t to the third over 3. 4 is a constant, so you can write that down. The integral by power rule of t to the first is t to the second over 2. Add 1 to the exponent, divide by the result. The antiderivative of a constant, in this case, would just be 4t, like that then. Okay? So that's what you would have for your antiderivative, and of course it's an indefinite integral, so you won't have the plus c like that. So what I'm going to do is just distribute through like this and write my final answer as 4/3 t to the third minus, and notice we have 4 over 2, so 4 over 2 is 2, so that would be 2t squared plus 4t, 4 times 4 is 16, and then plus c. Okay, so that's probably the best way to write the answers like that. Okay, so again, multiplying out the t minus 2 squared to get t squared minus 4t plus 4, and then applying the power rule and the integral of the constant 4. All right, so that's how that goes. Okay, now moving to the next one. I think I just made a mistake on the last problem, so I'm gonna erase this and show you what I think I did. Okay, I was being a little sloppy on this. Okay, well, let's see. So here's kind of what I did here. Let's this is okay. You write the 4 down. The antiderivative of t squared is correct. The antiderivative of t to the first is correct, and the antiderivative of 4 is correct, but it's getting a little sloppy, and this is where I messed up. So really, I've got 4 times 1/3 t to the third. 4 over 2 is 2, which I did correctly, but I didn't distribute right. Okay, so now if we distribute, we're going to get 4/3 t to the third minus 8 t squared, and finally plus 16 t plus c. Okay, that's better. Just getting a little sloppy with my distributive property. Happens when you skip a step and try to do something in your head sometimes. Okay, so the next one is another basic integral. So we're going to go ahead and let's break this up into 3 parts. So we would have the integral of 4 square root of x dx minus the integral of 1 over cube root of x dx, and plus the integral of 1 dx like that. Okay, now we're going to write these radicals as rational exponents. So I'm going to take the 4 out. That will be the integral of x to the 1/2 dx. Okay, this next thing here, I'm going to do something on the side here. You really have 1 over x to the 1/3. You know, if you're doing 1 over cube root of x, if you're doing that integral, you want to change it to that. And then you want to change it to x to the negative 1/3 dx. Just doing that to save a step here. So I'm going to have the integral of x to the negative 1/3 dx, and then finally the integral of the constant 1 dx like that. So you got to get this set up so we can use the power rule, and the power rule, again, you add 1 to the exponent and divide by the result. Okay, the power rule shows up all over the place. Okay, so let's do this carefully then. All right, so let's see. First integral right here. Okay, write down the constant 4. Okay, and then we add 1 to the exponent, so 1/2 plus 1, I'm going to use 2/2, so I have a common denominator, then divide by the result. 1/2 plus 2/2 is 3/2. Then we'll simplify that in a minute. Go to the next one. We have x to the negative 1/3. Add 1 to it. Add 3/3. The result is 2/3, so divide by it. And then finally, the integral of 1 is just plus 1x, and then we'd have our plus c. Okay, now this is just not simplified, so we need to do just some basic simplification. All right, so what we'd have is 4x to the 3/2. When you divide by a fraction, what are you doing really? You're multiplying by the reciprocal. Okay, so we got that. Okay, same thing here. This is x to the 2/3 when you add the exponents. And then when you divide by 2/3, that's the same as multiplying by 3/2. So I'm going to do that. And then I got plus x plus c. All right, now it's pretty easy to finish up. If I multiply these two numbers, looks like I'm going to get 8/3 x to the 3/2. The next part right here is just this, so that's done. That's minus 3/2 x to the 2/3 plus x and plus c. Okay, like that. So that would be the answer to that. So what I've kind of gone through on these problems so far is just a little bit of everything that, we see a logarithm, an exponential, a power rule showing up with radicals. These are just kind of a variety of types of basic antiderivatives that we looked at. Okay. Now we'll move to U substitution, where you do a little bit more advanced integration. Okay, so the way that I generally have been teaching this is an integral that's, doesn't follow a simple rule. It's got a structure to it. So the first thing you got to do is you got to figure out what you're going to set u equal to. And a good rule of thumb, if you have e, then a good rule of thumb is that exponent probably is going to be your u. But here's how you know, all right, so for sure. So let's go ahead and try u is x squared plus x plus 1, okay? And then that way we would just have e to the u, which we know how to integrate, so that's good. But the key is du, it's nice if du ends up being the remaining expression. Now, disregarding the e to the u would be what we would want in our integral. So let's see what we get. Du is just the derivative of x squared plus x plus 1. So we know the derivative of x squared is 2x, the derivative of x is 1, derivative of 1 is 0, and then don't forget the times 2x. So this is probably the simplest type of u substitution. Everything matches perfectly. Okay, so it just goes like this. When you get this u integral, you're going to have e to the u, okay, so that's going to be the u part right there, and that blue part, 2x plus 1 dx, is going to be du. So all you're doing is substituting, that is u, and then the part in blue is the du. That whole part in blue is the du. Okay, this is real simple. The integral of e to the u is e to the u plus c. Last step is always plug back in the u value, and you would end up getting the final answer to this problem would be e to the x squared plus x plus 1 plus c. Okay, so that is the antiderivative. That's the value of your indefinite integral. Okay, now one thing you can always do, I'll do this another time, you can check the answer of this problem. So if you did the derivative of our answer, the way we do a derivative of an exponential is it's itself, and then it's times the derivative of the exponent. The derivative of that exponent is 2x plus 1. Now see, that takes you back to the beginning, so it's pretty simple to, in general, at this level, to check your answers to your problem. Okay, now I'm going to do one more u sub, just review one more of these. Okay, so this one, let's try the bottom. So let's see what we get here. All right, so let's let u be t to the third plus 3t. All right, now, that would give us maybe a 1 over u integral or something, which makes me think of a natural log. But the key here is you're hoping that du is what's left over. What's left over is t squared plus 1 dt. Let's see how close we are. Okay, derivative of t to the third is 3t squared. Derivative of 3t is 3. So we're a little different. So I'm going to kind of write this like this. du is 3t squared plus 3. What we really wanted was du to end up being t squared plus 1 dt. Okay? Well, just ask yourself a question. This is an equation. You can multiply or divide both sides of this equation by anything except 0. So if you look at this, what you would do is if you divided both sides by 3, you would get this, see? Okay, so you would end up getting 1/3 du equals t squared plus 1 times dt. Okay, so that's what you kind of end up having now. So now your u integral goes like this. Okay, if you go back to our substitution, the t cubed plus 3t, that's u. Okay, and then the blue part, the t squared plus 1 dt, that's not du, it's 1/3 du. Okay, so that is the integral we're going to work out to get our answer. Okay, 1/3 is a constant. It's a great idea to just pull that out. So we would really have this integral. Okay, the antiderivative of 1 over u is ln, absolute value of u, and then don't forget your plus c. I docked you half a point if you forget your plus c, because you're wrong if you don't include that in there in an indefinite integral. Now we just plug in the u. The final answer will be 1/3 ln, absolute value, t cubed plus 3t plus c. Okay? And let's do a check. Let's just take the derivative of our answer. So 1/3 is a constant. Remember, the way you do the chain rule for a natural logarithm, it's 1 over the function times the derivative of the inside part, which is 3t squared plus 3. And of course, the derivative of c is 0. Well, so what happens on this then is this basically. If you look at this part right here that I'm highlighting, well, that just divides out the 3's. Okay, so what you really have is this. I'm going to write this as 1/3 times, and I'm going to factor out a 3 out of this part right here. That's the part that's in yellow there. Then I've got the leftover 1 over t cubed plus 3t. Look at that. We end up with t squared plus 1 over t cubed plus 3t. That's what we started with. Okay, so that's how simple it is to check and verify your answer. All right, so that'll kind of wrap up a good review of antiderivatives, indefinite integrals, and some u substitution. Okay, moving to the next thing, I'm going to look at a couple of application problems. We learned a little bit about optimization, so let's go over this optimization problem, which we looked at in class. So this says you're going to construct a box without a top. You're cutting squares of each corner of a flat piece of cardboard that's 30 inches by 16. Okay, so the way this starts off is the entire original side is 30 inches, and the width starts off as 16 inches. However, we're cutting off these values here. So this little piece here is no longer 16. It's 16 minus 2x, because we just chopped off, these two little corners that are x by x. Same thing happens here. This thing is no longer 30. It's 30 minus 2x, because again, we chopped off these two corners. Okay. All right, so I'm going to just put these dimensions here. So the length of this is 30 minus 2x. The width of this is 16 minus 2x. And the height of this is x. Okay, you need to have 3 dimensions to get your volume of your cardboard box. All right, now we're going to make the volume function. Well, we know the volume of this box is the length multiplied by the width, multiplied by the height. So we'll just do that. The length is 30 minus 2x, and then 16 minus 2x multiplied by x. Okay, now we can write the volume function. I said leave in the factored form, so we'll just write the volume function like that. I'm going to put the x in front. It does not make any difference which order these things are in. So that would be your volume function then. Okay? All right. So now what I'm going to have is we're going to use calculus to find the maximum volume of the box. Well, what we have to do is we have to do the derivative v prime. So we got to find v prime of x, and you got to multiply this out. You don't want to use a product rule or anything. You could. There's a way to do that. I think it's just as well to just multiply this out. So what I'm going to do is I'm going to just write down the x, and I'm going to go ahead and FOIL this stuff here. I'm going to do some of this at the side of my paper here. You got some pretty big numbers, so you can use a calculator. So we would have 30 times 16. So 30 times 16, I believe, is 480. Outside term would be 30 times negative 2 is negative 60x. Inside term, negative 2 times 16 is negative 32x. And then the last term is a positive 4x squared. These are like terms, so if I do 60 minus 32, that's 28. So I get 480. Whoops, hold on. That's two negatives, isn't it? I didn't see that. Okay. So I got two negatives. Yeah, so that is negative 92. Sorry about that. So we get 480 minus 92x plus 4x to the second. Now I'm going to just bring this over here, and then we'll just distribute the x through this. Then we'll be in a good form where we can do this derivative. So we have v of x is equal to 480x minus 92x squared plus 4x to the third. Okay, just distributing that out like that. All right, now that's the easiest way to do the derivative on this is multiply it out. Okay, so we're going to find critical numbers. So we're going to take the first derivative, which is 480 minus, and then 2 times 92 is 184x, and then that would be plus 12x to the second like that. Okay? Now we're going to do this. This is probably something that you might have a hard time factoring, so it's probably a quadratic formula problem. It's often good to see if these numbers divide by anything. They divide by 4. Let me see, 6. I'm just kind of experimenting with my calculator. I can take a 4 out for sure. So I'm going to take out a 4. So if I take 480 divided by 4 on my calculator, I would get 120 here. And then 184 divided by 4 would give 46x. And then 12 divided by 4 would be 3x like that. Okay, 3x squared. All right, now I'm going to set this equal to 0. And by doing this, what I can do is I can divide by 4, and then I have a quadratic equation that I can use the formula on. So I've really got 3x squared minus 46x plus 120 is equal to 0. So I'm going to go to the quadratic formula to find that value of x. So the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, in this problem then, we got this in standard form. You got to put the x squared first, then the x, then the constant. So a is 3, b is negative 46, c is 120, so we just need to plug that in. We'll use our calculator to help us with this too. So we'll have negative b is negative 46, plus or minus the square root of b squared, so negative 46 squared, minus 4 times a, which is 3, times c is 120, and that's all over 2a like that. All right, now I'm going to pull up my calculator, and what I'm generally like to do on this is just work out the what we call the discriminant, the part under the radical. So I'm just going to go ahead and put that in my calculator. Negative 46 squared minus 4 times 3 times 120, and then I'll record that. So that's 676. All right, so notice what I have is a negative, so that would be positive 46, plus or minus the square root of 676 over 6. Okay? All right, now the square root of 676 is likely, let's see what that is. I don't know what that is. Oh, that is a perfect square. That means that this would have factored anyway, so we get, I didn't know. So we have, this is equal to 46 plus or minus 26 over 6. Okay, all right, that kind of will give us a nice simple answer on that. So we need to go ahead and do two things. We need to do 46 plus 26 over 6. So I can do that with the assistance of my calculator. 46 plus 26 is what, 72? And 72 over 6 is 12. Okay, so that's one potential answer there. And then we also need to do x equals 46 minus 26 over 6. So that would be what, 20 over 6. And 20 over 6 you can divide by 2, so you would get 10 thirds. Okay, so we basically have two critical values. Only one of them makes sense though. So the thing is, 10 thirds is approximately, it's 3 1/3, so it's approximately 3.3. All right, now if you go back to your problem, one of these answers won't make a whole lot of sense, and let me explain why that is. So if you look at a rectangle, we started this problem off with a rectangle like this, and the dimensions were 30 inches by 16 inches. Okay, the 12 is too big, because what would happen if you cut out, if you did a square here that was 12 by 12, then you wouldn't have a square left over there, okay? I mean, you wouldn't, that's too big. Okay, it's way too big. So actually, the biggest that we can cut out is 6 by 6. Okay, if we cut out 6 by 6 squares, then we'll just have a flat sheet of paper. So basically, x needs to go between 0 and 6. That's where it makes sense between those two things. And actually, it's even more sensible if I put strict less than problems. Okay, and it's obvious. If you cut out a square 0 by 0, you're not going to make a box. If you cut out a square 6 by 6, you aren't going to make a box either. So the dimensions have to be between 0 and 6. Okay. All right. So now what I'm going to do on this is, now we can graph this on the calculator, and this is sort of a technology problem. So what I generally like to have students do on a problem like this is let's just graph the function. So I'm going to go back to the volume function we have, and I'm just going to put it in the factored form. So we have x times 30 minus 2x, and then we have 16 minus 2x. Okay, like that. And then our window is going to go like this. Okay, for a window, we're going to go 0 to 6, okay, because I just talked about the significance of 6, and we're going to scale that by 1. For your y's, just look at your table of values. So I'm going to go second graph, look at my table of values between 0 and 6. And notice what happens on this is this volume right here, these would be kind of the range of numbers on here. I need to check one thing here and make sure I put this in right. I may have made a mistake here because there was something popping up on the table I wasn't expecting, so I think I had an extra parenthesis or something in here. Okay, so I have x times 30 minus 2x, and then 16 minus 2x. Okay, now I'm going to go to my table. Okay, I guess I had it in okay. All right. So that was 30 by, oh, hold on. The 6th thing doesn't make any sense. It's 8. Okay. All right. And I don't know what in the world I was thinking on this. I knew that if x is 0, you don't make a box, so it has 0 volume. it's 8. I don't know why I didn't get that, so let me explain that again. This is ridiculous, too. You guys maybe are laughing at me on this one, or either you just didn't catch it either. So the idea is, hey, if this thing is 16, half of that would be 8. Okay, so if you cut out two 8x8 squares, then you wouldn't be able to make a box, and you couldn't make, the problem doesn't make any sense once you get past 8. Okay, all right. So sorry about that. That should have been an 8. Jeez. Okay, so I'm going to make my window go 0 to 8. Again, if I look at my table, this is how I caught my mistake, because I knew that's what would happen, is eventually this thing would become 0. The biggest number I see is 720. So I'm going to go 0 to 800 and then scale that maybe by 100 like that. Okay, so I'm getting this window just from looking at the table of values to get those y values. Now I'll graph it, and then there's my curve. Okay, so what's going to happen on this then is we have a maximum, and let's see if we have this. Let's see, we're thinking that 10/3 is the maximum. So let's just trace at 10/3. So I put 10 over 3, and sure enough, that's the maximum. And the nice thing about doing the graph to finish up the problem, number one, you can tell visually that you found the maximum correctly without doing a sign chart in calculus. But also, this right here is the value of x, and that is the volume. Okay, so that answers the question. The maximum volume is 725.93 cubic inches if we round, and then the dimensions we'll just say is about 3.3 inches by rounding like that. Okay, so that's a good way to do that problem. All right, but you do have to find the critical number, and you do have to use quadratic formula or factor to get that done. But I highly recommend that you do these technology problems with your calculator as much as you can. Okay, all right, moving on. I've got a couple more to look at to wrap this up. So let's take a look at this one. So this one says a manufacturer incurs the following cost function in producing X water vests, ski vests, in one day. All right, so that's a cost function, and we're given a domain from 0 to 150. So we're going to find the average cost function. So remember, we've done this quite a bit. The average cost function that we represent by c bar of x is nothing more than taking the total cost function and dividing by x. Okay, so I'm just going to do this. I've got 0.05x squared, and I'm just going to split it up and divide each piece by x. We're going to have to do the derivative when we find the minimum average cost anyway. So we've got a little algebraic simplification. That's going to be 0.05x. Here the x's drop out, giving you plus 20. And this last term, since we're going to do the derivative, I would slide that to the top and make that x to the negative 1. So a good way to write your average cost function is c bar of x is equal to 0.05x plus 20 plus 320x to the negative 1. Okay, so there is your average cost function. Okay. All right, now we're going to use calculus to find the minimum average cost. So it's the typical things we've done. You want to start by doing the first derivative of your average cost function. So that would be the derivative of 0.05x is 0.05. The derivative of 20 is 0. Then we do the power rule here, so that would be minus 320x to the negative 2. Okay, so I'm going to write this as c bar prime of x is equal to 0.05 minus 320 over x to the second. Okay, so that's what you do. Now you want to set this equal to 0 to find a critical value. So we'll have 0 equals 0.05 minus 320 over x squared. You need to solve this equation. Probably the best way to do is to add 320 over x squared to both sides. So I would get 320 over x squared is equal to 0.05. Now you could cross multiply this if you want to. That's a good way to do it. So you would have 0.05x squared equals 320. Divide by 0.05. Okay. And then probably the square root property. Okay, so let's see. We'll do 320 divide by 0.05. And that'll give 6,400. So we have x to the second equals 6,400. Then we can do the square root of both sides. And that one comes out even, so that is 80. So if you were to go through and do this then and just do the square root of 6,400, you can do that in your head if you want to. It just gives 80. Okay, so that is 80. So that is the critical number. Now, if you were going to continue with the sign chart, then you would just go like this. Okay, now this problem is defined at the beginning between 0 and 150. Okay, so we just found our critical value to be 80. So if we take our derivative is, we got 0.05 minus 320 over x squared. So if we plug test points in between 0 and 80, if we plug a 1 in, we would have 0.05 minus 320 over 1 squared. That's negative. Function decreases. If you plug in 81, you can do this on your calculator too if you want to. You would have 0.05 minus 320 over 81 to the second. Kind of hard to do that in your head, but let me show you what happens. So 0.05 minus 320 and divide by 81 to the second. And that gives a positive. Okay, so that means that the function is going to increase. So you're going to have a function kind of decreasing, hitting the low point, and then increasing like that. So yeah, okay, so we do have a minimum that occurs there, all right? So now, step 4, and then we'll check all this on the calculator. We know x equals 80 provides the minimum. So let's just go back to our average cost function. So our average cost function at 80, let's go to our answer to part 1, which is 0.05x plus 20 plus 320 times 80 to the negative 1. You're going to use your calculator anyway, so I'm just going to plug it in like that and do that on the calculator. So I have 0.05 times 80 plus 20 and then minus 320 times 80 raised to the negative 1 power, and that gives 20. Okay, so that gives $20 as our minimum average cost. Okay, all right, so I'm going to record that, then we'll do a graph, and the graph is intending to verify this then. Okay, okay, so let's kind of see what we got now. Now we're going to do a graph, and I've been kind of talking a lot about graphs here. There's this tendency for students to put stuff in the calculator and then there's my answer. I mean, that's ridiculous. Okay, you got to get better than that. That's, like a lousy piece of art. You got to scale your axis and everything there, so I want to make sure we do that. All right, so let's throw this in the calculator. What I'm going to do is put in the answer to part A, the average cost function. Might as well just put it in like that. So 0.05 times x plus 20 plus 320 and x raised to the negative 1. So we want to get that put in. Need to come up with a good viewing window. Now the good thing about the problem is they told you to use 0 to 150. So for our window, I'm going to go 0 to 150. A good scale on that might be by 10 or, I don't know, 10 maybe. Or we could go by 50 also if you wanted to. And then, you want to just kind of take some values here. You can always look at your table and get a sense on this. Now what happens with this is it starts real big at 340, then you'll see these numbers getting smaller for a while. Eventually they'll start getting bigger again. And when you get to 80, that's where they're going to start getting bigger again, since 80 is our critical value. So for that reason, let's do 0 to, let's just do 400. Oh, hold on. No. I already got the x right. So 0 to 150 by a scale of 10 for x. I was going to go 0 to 400 by a scale of 100 for my y values then. Okay, so if I type graph, okay, that's pretty good. That's not great, but it's fairly good. Okay, so let's go ahead and let's put this up here. You can kind of see the minimum here, and if you trace it 80, that's showing the minimum of 20 like we got, so that's not bad. Now let me show you what I would want for a graph. Okay, I mean, you're using your calculator. There's absolutely no reason why your graph shouldn't be, really accurate. Okay, so we're going to go to 150, and we said we'd scale by 10. So I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then 10, 20, 30, 40, 50 would be a logical way to do that. You want to label what the meaning of the x-axis is. This is x is the number of ski vests. Okay, now for our window for the cost, we decided to go to 400. So we can decide how we're going to scale that. Okay, so just kind of spread it out. I'm going to just kind of figure out, maybe I'll go 1, 2, 3, 4, that's 100. 1, 2, 3, 4, that's 200. But you got to scale this. 1, 2, 3, 4, that's 300. It's just a good idea to spread this out. 1, 2, 3, 4, 400, like that. And then this is the average cost. So that's what you have to have. I mean, you have to have that stuff on your graph. You have to. Now, the next thing I would suggest that you do is get about 3 points. Well, we know that we had the point 80, 20, which is, and you just can estimate this. Here's 80, 20 is about in here somewhere. So I'm just going to label that as the point 80, 20. Now just get a few more points. Just trace it 150 at the end of your graph. That is 29.6. So just do that. Put a dot, estimate where it is. It doesn't have to be perfect. But 150 and about 29.63. Okay. And for the next one, let's just pick one more point. Let's just trace it maybe like at 10. So if I trace at 10, we're at 52.5. So that would be like right around here somewhere. Just kind of ballpark estimation. And then from there, you can graph this. So you can just kind of show that that's a minimum, starts going up a little bit, and starts heading towards the y-axis like that. Not perfect, but it's got labeled points. So that's what your graphs need to look like. Okay? Okay, so the last page, moving to the last page, and finish up this last problem I wanted to review, is a differential equation. So I want to run through this. So with this one, let's see. This is the marginal price. It's a derivative. And this is X bottles of shampoo. And this is the marginal price. So we're going to find the price demand function. So we're going to find P given the derivative if the weekly demand is 150 when the price of the shampoo is $8. So the first thing you want to do on this type of differential equation, let's just write it down. We have P prime of X equals negative 6,000 over 3x plus 50 to the second power. Now we need to do the integral of both sides. Okay? Now we know the integral of a derivative is just the function, and that's what we're trying to find anyway. And then with this one, let's pull out the constant and have negative 6,000 times the integral of 1 over 3x plus 50 to the second times dx. Now this is a u substitution integral. That's one that you would probably want to u sub. So let's go to step 2 and let's just focus totally just on this integral. Don't forget your 6,000. Okay, it's easy to forget about that if you pull it out. Okay, so we're going to do this by u sub. Okay, so the way to do this one would be, let's kind of get this set up. We're going to have u Well, the only thing we could probably do is just set it equal to that denominator right there, and just the inside part like that. So that's going to be 3x plus 50. Okay, du, the way that we've kind of been processing this is we would like for du to be 1 dx, but it isn't. The derivative of 3x plus 50 is 3 times dx. So we want this to really be du equals 1 dx. Well, that just means we have to divide by 3. So I'm going to divide this by 3, divide that by 3. So I will get 1/3 du is equal to 1 dx. Okay, now I can put this all together. So basically, the 1 dx is going to be 1/3 du, and then the 3x plus 50 is going to be u. So we end up with the integral negative 6,000 times 1/3 du for the blue part over u squared. Okay, that's an integral that we can definitely manage. Okay, all right, so let's go ahead and let's go through this now. Okay, well, we can pull the third out, so you would have negative 6,000 times 1/3, and then you'd have the integral. Now you want to bring the u to the second up to the top so that you can use the power rule. Okay, negative 6,000 over 3, that's negative 2,000. And then the antiderivative of this would be u to the negative 1 over negative 1 plus c by the power rule. These two negatives divide out, so you would get 200 or 2,000 over u to the first plus c. Okay, so that's step 2 is to do that. Now the other thing we need to do is plug back in u, and then we still got one more thing to do here. So the result of step 2 is you would have p of x equals 2,000, positive 2,000, over 3x plus 50 plus c. Now that's a u sub integral. So I'm going to go back to step 1 and write that down. So I have the price demand function, the general solution of this differential equation is going to be this. Okay, so we're about halfway done now. So you have to integrate. Now that one just happened to be a u substitution because of that 3x plus 50. Now you have an initial condition. This basically says when you have a price of $8, the demand, which is x, is 150. Now you can plug that in and you can use this to find c then. Okay? All right, so we're going to find the price demand equation for that value. Okay, so what we'll have is 8 equals 2,000. This is really step 3 now. Over 3 times 150 plus 50 plus c. Okay, I'm going to do a couple things on my calculator. So if I do 3 times 150 plus 50, that's 500. So I have 2,000 over 500 plus c. So that's 8 equals 4 plus c. You can subtract 4 from both sides, and you get c is 4. All right, so the final answer, the official price demand function is p of x is equal to, the answer we got here, 2,000 over 3x plus 50 plus the c we just found. C was 4. That's it. All right, that's it. That'll wrap up my review. So thanks for watching, and study hard and work the problems out. Hope you do well. Bye now.